Well, hello everyone. My name is Anastasia Chavez. I use she, her, pronouns, and I'm an assistant professor from St. Mary's College of California. I'm very honored to be asked to be an upcoming speaker for Café con Leche. So thank you so much to the organizers for the invitation, and thank you for your time to watch my video, either normal speed or 1.5 or even double perhaps, however I sound at that level. But I'm excited to talk to you today about a project I've been working on for a little while that involves two interesting players that sort of get mashed up together in the world of geometric combinatorics. So we'll be talking about valuation polytopes over height 2 posets. And I should also note that this is research that's been partially funded by a National Science Foundation grant. So I'm been very thrilled to be working with the following folks on this project. We have Federico Ardila, Jessica De Silva, Jose Luis Herrera, and Andres Vindes Melendez. And like I said, we sort of have two key players for the project. So let me introduce the first player. We're going to be talking a lot about polytopes. So how do we describe a polytope? Well, you have two different definitions. One is in terms of vertices. So we could take a bunch of points in space and then imagine wrapping them with a rubber band and then letting that rubber band snap. And the points that are left at the corners of this shape we call the vertices, and then the shape itself we call the polytope. And that action of sort of letting the rubber band snap is like taking the convex hull of those points. So you can imagine convex hull means that if you and I were living inside this polytope, no matter where we were, we'd always be able to see one another. So we can think about describing a polytope in that way. Equivalently, we can also describe a polytope in terms of the finite intersection of half spaces. So if you take a collection of finite collection of half spaces, and then you just look at their intersection, then that space that's cut out or carved out by those half spaces also describes a polytope. And then you can see here as an example on the slide, the same polytope given to you in terms of the half space description or the vertex description. And we'll be spending most of our time talking about vertices for polytopes. Now, the second key player for this project is a partially ordered set, or poset for short. So we think about a poset, or we define a poset as a collection of elements that have a partial ordering on them. That partial ordering has to satisfy a few requirements, a few conditions, but we won't get into that today. We can also represent our poset in terms of something called a Hasse diagram, which are what you see on the slide here. So the Hasse diagram gives us a way to show when an element is less than another element in our poset. We'll place an edge if, let's say, for example, H is less than E in the poset. If you have two elements like E and F that do not have any type of order between them, we call them incomparable, and there's no edge in the Hasse diagram to represent that. Now, you might consider, what about edges between other elements that clearly one is less than the other in the poset? For example, B is larger than H, and so you might consider putting an edge between those two elements. But since we have another element E that lives between them, we're only going to place edges between the elements that are sort of minimally ordered. So we can find our way from H to B, but we'll make sure that E is the thing that we place the edge between. All right, so when it comes to a poset, there's lots of different things that you can define or consider. A couple of things I want to mention because they'll show up a little bit later are the following two operations on elements. So if I take two elements, let's say C and F from our poset, then I can compute something called the join. So this is going to be an element that is larger than both of them. So we're looking for an upper bound, so something that's larger than both C and F, but it's the smallest, right? It's the least of among all those options. So I can see that B and D and A are all larger than F. A is also larger than C, and it happens to be the smallest value that is both larger than C and F and sort of minimal among them. And since we're at the top of the poset, we really don't see how we could do any better than that. Now we could also imagine, what if we take those two elements, C and F, and we're going to look for something that is smaller than both C and F, but it's going to be the largest value such that it's the smallest. And here we can see that E and G, H are all smaller than C. H is also smaller than F, and H happens to be the element that is less than both C and F and the largest such element. All right, so we can compute these two things called joins and meets of elements in the poset. And here's just an example of how you might consider taking the join and the meet with an element that is comparable. Okay, so now that we've got that definition in mind, another thing we could define given a poset, if it satisfies the following three conditions, is then we actually have a special type of poset called a finite distributive lattice. So your partially ordered set has to first contain a finite number of elements. If I were to consider every pair of elements in my poset, I will always be able to compute a meet and a join. And then the last condition says if I take any triple of elements, and then I have this type of collection of operations of meets and joins, that I should be able to distribute my meet across and end up with an operation that makes sense. Right, so this distributive property should make sense in my poset. All right, so if you have a poset that satisfies those three conditions, then we can call it a finite distributive lattice. Great. So one thing we can define for a finite distributive lattice is a particular mapping or placing of values onto the elements called a valuation. So this is going to be a function or a map that starts with your lattice and sends values to the real numbers, and it has to satisfy the following equality. So the value placed on the join of two elements, A and B, must be equal to the value placed on A plus the value placed on B minus the value placed on their meet. All right, so as long as you have a map that satisfies this equality over a distributive lattice, then what you have is a valuation. All right, so now we've got our finite distributive lattice with valuation placed on it. What we're able to do from here is sort of find our way through a few different results that allows us to finally get to the polytope that we're interested in, called a valuation polytope. So first, in the early 80s, we have Gessinger that defined the valuation polytope to be the convex hull of the set of valuations over a finite distributive lattice, such that the values of that map have to live between 0 and 1. Okay, so now we've got our first instance of a valuation polytope. Just a few years later, Dauberton showed that the vertices of this valuation polytope are exactly the valuations that take on 0 and 1, right? So you don't have these values that somehow live between 0 and 1, but are exactly 0 and 1 values. Great. So then after that, we've got Dauberton using the fundamental theorem of finite distributive lattices to define the valuation polytope for any poset. So we can drop the distributive lattice condition on our poset and actually define this valuation polytope over any poset that you're interested in using the downsets of that polytope. So I'm not going to go into what a downset is, but you can sort of imagine all the values that are less than a particular set that you care about. But using this particular description of subsets of your poset, he was able to show that the valuation polytope Gessinger defined and then this new description for valuation polytope over these downsets are actually linearly equivalent. And so when we think about results for the valuation polytopes from one or the other version of these things, that sort of in essence, they're describing the same information. So then finally, Dauberton provided a very nice user-friendly vertex description using just the chains of the poset. And this is going to be the definition that I introduce next and the one that we utilize throughout the results that I plan to show you today. So the description looks like this. We take any poset, right? We drop the distributive lattice condition. And if you take a point in your polytope, your valuation polytope, you know it's going to be a vertex. If and only if, you can think about describing that point as values that are associated from chains in a poset, where you can consider the empty chain if you'd like, or some chain with values in it, some poset elements in it, such that the entry the entry associated with that particular element is either 0 if it doesn't show up in the chain, or it's -1 to the position that it does show up in the chain. Okay, so it maybe seems a bit complicated now, but let's take a look at the following example. So we have our poset that we've been looking at, and let's consider the chain that goes A, B, F. I meant to fix that. Okay, here's a little error to make it feel real. So this should be the chain A, B, F. All right, so what we're going to do is first count from 0. So A is in position 0, which is why we've got a -1 to the 0th power. So that's going to be the value we plug in for element A. And then B is going to be in the first position, which is why we have a -1 to the 1 power there. And then the rest of these entries are C, D, A, B, C, D, and E. C, D, and E do not show up in the chain, which is why they get a 0. And now we have F, which is in the second position, right? We went 0, 1, 2, which is why we've got -1 to the 2nd power. And then G and H do not show up in the chain, so they get the entries 0, or value 0 in their entry. All right, which gives us the following point in space associated to that chain. Great, which is how we're then going to say, here is a poset that we care about, translate or rewrite all of the chains in this poset as 0, 1, -1 points in space. We'll take the convex hull of those points, and then what we're looking at is a valuation polytope over that poset. All right. So why might somebody consider asking this kind of question? Well, often we find really interesting problems to think about from Richard Stanley's Enumerative Combinatorics Volume 1 or 2 books. And this is precisely where we found this problem. So if you go to chapter 4, question number 58, at least in the version that I have of this book, you'll see the following parts of this problem. There's a few more because you can see this goes from C to I. But in this problem, he's providing the definition that we just walked through, right? This vertex description of the valuation polytope in terms of chains of a poset. And then he's asking, can you show that the dimension of the valuation polytope is precisely equal to the number of elements of the poset? Great. So that's something we know already, that the dimension of the valuation polytope should be the size of the poset. And then he's asking to compute something called the Ehrhart polynomial, which is like a polynomial that sort of does some encoding of volume information from your polytope. And in particular, asking for this description for the sort of simplest poset you could imagine, which is just a chain. So just a line of elements all ordered nicely that way. Okay, so once you have some sense of what this question's asking and sort of playing around with this interesting but pretty simple poset, it seems fairly natural to then say, do it again, but with a poset that you care about. So what are some other things that we might be able to say about the valuation polytope in general, given some general poset or other types of posets? Is there some nice combinatorial interpretation of the volume? Can you maybe describe the coefficients of this Ehrhart polynomial? For example, are they perhaps non-negative? This question here of are the coefficients of the Ehrhart polynomial non-negative is often a question people ask, because when we see values that are non-negative, we think they might count something, right? Especially in combinatorics. And so that's really the reason why we start to ask for non-negativity, and then that gives us the green light to start to look for combinatorial interpretations. All right. So this sort of, we found this problem. This sort of sent us off in a direction. And from there, we said, okay, what's a poset we might want to consider? How about we consider something that sort of looks like a zigzag or maybe a fence, right? These are two names that have been applied to this poset in the literature. We're going to stick with zigzag poset. So this is a poset of elements that sort of do this. 1 is less than 2 is less than 3 is excuse me, 2 is greater than 3, 3 is less than 4, 4 is greater than 5, right? So it sort of does this alternating greater than less than behavior in the poset. So we've got for 2 elements, 3 elements, and 4 elements examples of what those zigzag posets look like. Now for each one of these posets, we just saw that Dobbertin gave us a really nice way to describe the vertices associated to the valuation polytope, right? And so let me just write down what the chains look like here. So we've got the chains associated to the zigzag poset with just 2 elements are the empty set, the chain that contains 1, the chain that contains 1 and 2, and then the chain that contains 2. So when we add the next element to get to the zigzag over 3 elements, you can see that the chains that we saw from the previous poset, those stay on. And then now all we're doing is adding the chain that has 3 and 2 in it and 3 itself. So we've added 2 new chains there for just adding a single element to the poset. And now if we play the game again, we're going to add another element. So now we have 4 elements in our zigzag poset. Again, all the previous chains stay on, and we're only adding 2 more that include the element 4, right? Either the chain 3, 4 or the chain 4 itself. So you can already see here that we have a nice recursive description for chains in the poset, but those also give us, and here I'm going to reveal the corresponding vertices for the valuation polytope. And so this actually gives us a nice way to count recursively the number of vertices for the valuation polytope over a zigzag poset. Great. Now here's a couple of examples, or excuse me, 3 examples of what the polytope associated to these valuation polytopes look like. So for 2 elements, you're going to get this sort of parallelogram looking object. For 3 elements in your zigzag poset, you get something that sort of looks like maybe a tent. And then in 4 dimensions, you have this thing here, which is called a Schlegel diagram, and it's a 3-dimensional way of realizing a 4-dimensional object. Okay, so I do want to just point something out here because it's going to come up a little bit later. But when we think about moving from one dimension to the next dimension up, right? In the previous slide, we saw that there's sort of this recursive behavior. Some of the information from one dimension sort of hangs on in the next dimension. And in this case, it sort of looks like the vertices here should show up as vertices over here. And in fact, they show up as the bottom 4 in this picture. And then these 6 should show up somewhere over here. But I want us to first note that if we take just the zigzag poset with a single element, then what that looks like is the line segment connecting these 2 points here in the middle of our 2-dimensional valuation polytope. And so then when I add this new element 2, I'm actually adding the 2 points that look like the one above and the one below the line segment of the dimension 1 polytope. So this behavior, we call it a bipyramiding, because it's like we've pyramided or created a pyramid on one side of the polytope and then a pyramid on the other side of the polytope. And now when we move from dimension 2 to dimension 3, the 2 new points that get added are these 2 here, which actually live on one side of the polytope from before. And we're going to call that a tenting. So when we go from odd dimension to even dimension, what we see is a bipyramid behavior. And when we go from even dimension to odd dimension, we're going to see a tenting behavior. So we either have 2 vertices added on opposite sides of the polytope, or two vertices added on the same side of the polytope. Okay, so this bipyramiding versus tenting behavior, and that'll show up later in some of our proofs. All right, but again, that recursive behavior is pretty important, right? So we want to note that for later usage. And then now that we have a good understanding of what these valuation polytopes are defined, how they might look, let's just sort of back up for a moment. And I want to give a list of some questions that one might ask. If you're at all interested in just thinking about polytopes, you come across a polytope that someone hasn't understood very well, this is a list of possible questions you might want to ask. And I just want to give a shout out to Ben Braun because I saw him present this list in a talk recently, and I was like, this is great. Not only is it great because it gives you sort of a roadmap of things you might do, but also it was a roadmap that we followed. So it was a nice confirmation that we've asked some good questions. So if you consider a polytope, you might ask things like, can I describe the vertices, right? One of the questions we've kind of already seen was answered by Doberton. Now, vertices are something that's called a face of dimension 1. And you could think about faces of various dimensions for your polytope. If your polytope lives in d dimensions, then you can ask for the faces that are d minus 1, so 1 dimension less from the dimension of the polytope. We call those facets. So these are kind of the extreme faces of your polytope. Can you give a description for those vertices or those facets? Maybe you can find interesting or effective formulas for the volume of your polytope. There's something called an H star vector for your polytope. Can you classify what this looks like for your specific family? Maybe you can give combinatorial interpretations for the values that show up in this thing. Perhaps you can investigate inequalities for the coefficients that show up in something called the H star polynomial, which we'll show a little bit later in this talk. You might find out that you have some unimodality behavior, log concavity. Maybe your polynomial is real rooted. There's something called gamma non-negativity. We won't get into that today, but there's a lot of properties about your polytope that are nice to know. You might investigate something called a triangulation, which we'll get into in a little bit, but you could imagine chopping up your polytope into nice pieces and asking, can you describe this behavior? Is there some nice structure going on there? And then maybe you might think about classifying your polytopes in some way. All right, so this kind of gives us a nice framework for how we might think about polytopes. And let me just give you some of the first questions that we thought about when we first started this project. So definitely, how big is your polytope, right? What's the volume of your polytope? Or in our case, we're going to ask for normalized volume, which means we take the Euclidean volume, so sort of what you'd imagine if you were to like integrate over some space and come up with the volume of your shape, multiplied by the dimension that it lives in, factorial. So that's what we call the normalized volume. What about if I cared to count how many vertices, how many edges, how many two-dimensional faces, all the way up to the dimension 1 less that your polytope lives in, right? So we call this sequence of numbers an F vector for your polytope. Maybe you can describe what this F vector is for the valuation polytope over the zigzag poset with n elements, right? This is a question we asked ourselves. And then again, if I want to start to get into describing the Ehrhart polynomial or these H star polynomials, right? Some of these other questions that in a sense are encoding the volume information of your polytope, what can we say there? Right, so we're going to kind of dig in a little bit deeper into what that looks like. All right, so first, let me go ahead and answer this question about faces and facets of our polytope. So we already computed the number of vertices, right, when we went through understanding the vertex description in terms of chains, and we saw every time we added a new poset element, we just added 2 new vertices. So we expect there to be 2 times the number of elements in our poset, many vertices. Now, we also have a nice polynomial formula that gives us the number of edges for the valuation polytope of the zigzag poset. And then we also have some nice formulas here that tell us how many facets, or the dimension n-1 faces of our polytope. Now, what's kind of interesting is that each one of these computations actually uses slightly different information or approaches to prove. So we saw the recursive description for the polytope was helpful to find the number of vertices. The number of edges is computed using an edge description that we give, which I'll show on the next slide. And then the facets are actually enumerated utilizing the downset description that I kind of glossed over a little bit earlier, which I'm still going to leave on the table. So feel free to ask questions if you'd like later. But let me sort of dig into this edge description here that we use in order to come up with these formulas for the number of edges of our valuation polytope. So I really like this description for two reasons. One is it's a description for the valuation polytope of any poset of height 2, right? So we've kind of been thinking mostly about just the zigzag poset, but if you have a poset where you have one level of elements and then another level of elements and some relations between them, we call that height 2. This is the thing that tells you how to describe the edges for the associated valuation polytope. Okay, so that's my first reason why I like this result. And the second one is because it's in terms of the chains of the poset, which is really nice, given that we know that the vertices can also be described in terms of chains. So what we're looking at here in this result is that it tells you which pairs of vertices in your valuation polytope will not form an edge, and then all the rest of the pairs do form an edge. So sort of these obstructions to edges look like if you take the origin and then the point formed where the ith entry in that point has to be a 1, and it's going to be a 1 for a chain that comes from a lower element, right? So something that would have something that lives above it, right? So that's what we consider a lower element. And in that entry, it's just going to be 1 in that position and zeros everywhere else, just because it's a chain of size 1. So that pair of vertices does not form an edge. And in terms of the picture, it's something like the empty chain coupled with an element that is lower than other things, but it's just a chain of that single element. Now, the other pair is going to be a chain like JK here in this example. And then if K, we need K to cover some other element I, so it's going to be the combination of the chains that's KJ and the singleton chain with just I in it. That also does not form an edge. And then we have a similar combination of chains where we have a chain here where J is the top element, and then we consider the chain with just J in it. That pair of vertices will not form an edge. And then finally, we have the two chains like J1, I1 forms a chain, J2, I2 forms a chain. And we just need that we have this ordering as well so that J2 does cover I1, J1 does cover I2. So it kind of forms this bow tie ordering. So if we have two vertices that correspond to chains like this, they also do not form an edge. But like I said, all remaining pairs of vertices do form edges. So we have this nice sort of obstruction to edges in terms of chains here. All right. So we've talked about some values of our faces and how we might enumerate them. Let's move on to how we might think about the volume of this valuation polytope. So we have a nice formula here that tells us that the normalized volume for the valuation polytope is going to be a power of 3 when we have odd number of elements in our poset. And it's going to be a power of 3 times 2 when it's an even number of elements in the poset. So how we prove this is first we show that the valuation polytope over the zigzag poset actually has a really nice triangulation, right? So if we think about taking this valuation polytope and chopping them up into shapes called simplices, so these are going to be sort of the higher dimensional version of a triangle. I want that all of these simplices have normalized volume 1. So that's what we mean by unimodular. And this subdivision then becomes really nice because if I can chop up my polytope into these simplices of dimension of normalized volume 1, all I need to do is count how many simplices I have, and then that tells me the volume of my polytope. So by showing we have a unimodular triangulation for our valuation polytope, all we need to do is find a triangulation and then count the simplices. So for example, if we consider this valuation polytope for the zigzag of 3 elements, then a example of a triangulation, a unimodular triangulation, is drawn here. And what's nice about this triangulation, something that we like, is that each simplex that we use contains the origin. The origin is this back corner point, and you can see that the back corner point is a vertex for each one of the simplices in this triangulation. Okay, something we utilize later. All right, so then now that we have that, we can basically use a recursive description to show how we count these simplices. So I'll just give you a taste of what that looks like. If we consider the chains for the 3-dimensional valuation polytope, you can see them listed here. The picture we saw in the previous slide is actually the collection of each one of these vertices to describe each one of those 3 simplices, and you can see them listed here. All right, so then when we add the new element to the new element to the zigzag poset, it's going to include these 2 new chains into that list of chains. And since what we're doing here is going from odd to even, that's the case when we say take the polytope of odd dimension and we do the bipyramiding. So we include now a vertex on either side of the polytope and we do a coning over. And this actually gives us just a doubling of the simplices that we used before. So you can see the simplices from, or the vertices used in the simplices from above here, and then we just attach a new vertex, and then it creates a simplex in 4 dimensions now for each one of those sets. And then same on the opposite side, right? So we take the vertices of the previous simplices and we just attach a new vertex, and then now we have a doubling there. All right, so to get the other count, right? So this is the 3 to some power times 2. That's how we get our going from odd to even case. To get the other count, what we're needing to do is skip even dimension and go from odd to odd. So we'll start with our 3 simplices here from dimension 3. When we skip, we're going to add 2 and then 2 more, so a total of 4 new vertices or 4 new chains to that list, which you can see those values here. And so then when we look at the collection of simplices, what we're doing is, again, it's that bipyramiding and then we're tenting. And so really you're having to add 2 new vertices to create a collection of simplices, and it just so happens that they look like this. So we end up with the vertices from the original simplices plus 2 more. And it's the pairs that you see here that do the job. And then yes, it's some work to be able to show that this recursive behavior makes sense, but this particular triangulation that's unimodal gives us a really nice way to count triples, right? So we go from 3 to the power 1 to 3 to the power 2 down here, many simplices, and then every time we jump odd dimension, we'll see that tripling happening. Great. So now we've got a nice description of the volume. Let's dig in a little bit further into this concept of Ehrhart theory. So when we think about what is called the Ehrhart polynomial, first off, it's a function. So it's a function that counts the number of integer points in dilates of your polytope, right? So we have a polytope P. We multiply all the values in P by some value T. And then we take the intersection with the integers, which just means tell me all the integer points that live inside this dilation of my polytope, right? And as T varies, then this thing turns into some kind of a function. It's actually a big result by Ehrhart that shows this is indeed a polynomial that you're going to get. And as an example, let me just show you if we were to take the the unit square, right? So we have our unit square down here. If we dilate it, we multiply all the points by the value 6. That's how you end up with this larger 6p dilation here. And you can count, right? How many integer points lie inside this square? Well, it's 2 times 2, right? It's 2 on the x-axis, x1 axis, and 2 on the x2 axis. We multiply those two together, we get 4. If I look at the dilation of 6, it's 6 points plus 1, or 7 total, times another 6 plus 1, or 7 total here, to give us the 49 we expect there. So in general, we're going to get t plus 1 times t plus 1, or t plus 1 squared, as the formula for the lattice point enumerator, right? Or the Ehrhart polynomial for the polytope that is the square. Okay, so this is the kind of information we're looking for, is this type of polynomial that describes or encodes this sort of count of integer values in your polytope. Now, you can take that polynomial and plug it into a generating function, and then it spits out, after some work, right, and some nice theory and results, it spits out this really nice rational polynomial. The polynomial on top is actually also something interesting people like to study. This is the H-star polynomial that we referred to before in our list. So one question would be, can we describe this lattice point enumerator, right, for our valuation polytope? And can we actually give a description for this H-star polynomial as well? And in order to do that, we're going to use a nice description from Stanley that shows that the coefficients of this H-star polynomial are actually positive for integral polytopes, which means there's going to be a description there, and we just got to figure out what it is. So in order to tackle some of these questions, we're going to actually need to jump ship a little bit. So we're going to dive into something called a root polytope, but it turns out that this is really a nice lens to be able to see our valuation polytope through. So let me introduce what a root polytope is. So we consider a graph, okay, so a collection of points in space with edges between them. It's going to be oriented, which just means the edges actually tell us how to move through the graph. And it's going to be acyclic, which means that if I were to follow the edges through my graph, I'll never fall into some kind of a cycle or a repeating of vertices in my graph. Okay, so an example of an acyclic oriented graph we can see here is the complete graph on 3 nodes, or K3. And it's oriented as 1 goes to 2, 2 goes to 3, and also 1 goes to 3. So we can see that it's acyclic. I never follow edges around in the arrows and end up with some kind of a loop. All right, so we have that type of graph on a set of n vertices, vertices for the graph, and then we can define the root polytope to be the convex hull of the origin with vertices that are encoded by edges in the graph. So if you have an edge that goes from I to j, then you're going to have a point that has 1 in position I and -1 in position j, 0 everywhere else. All right, so this gives us a polytope that's over a subset of endpoints of positive roots for a root system of type a sub n minus 1, in case that's interesting to you. But really for us, it just means that if we can think about some kind of acyclic oriented graph, then we can generate these really interesting polytopes that have graphs associated to them. Okay, so how do we find this in our valuation polytope? So you see the zigzag polytope, or excuse me, the zigzag posets with 2 elements, 3, and 4 elements. So to create the type of acyclic oriented graphs that you see on the right side, what you could imagine doing is taking your poset and just stretching it out. And if there's an element less than another one in the poset, then it's going to be an arrow in the graph from that vertex to the other vertex. So let's take the poset that's got 1, 3, and 2 in it, like you see here. I stretch that out, so now we see the 1, the 3, the 2, with the arrows both pointing to 3, since they're less than 3 in the poset. And then once we do that stretching out, we add a new vertex that everybody is oriented to. We'll call it adding a sink. Okay, so you can see that for each one of our zigzag posets here, we'll stretch them out and add a sink and make sure that the edges are oriented properly. So from there, we're actually able to say, start with your valuation polytope, create these acyclic oriented graph, and now generate the polytope. So I show this picture because here is our zigzag of size 2 with the associated valuation polytope. Here's the graph that you get when you play the stretching and add the sink game. And then here is the polytope, the root polytope associated to that. And hopefully you start to see some similarities, right? Even the vertices look very similar with just some changes at that last coordinate, which is something that we are able to prove is actually true for any height 2 poset. If you play this game of changing the poset into a graph, then you can create a root polytope that is integrally equivalent to the valuation polytope over that poset, which means, so why would we go to all this trouble? Well, they are of the same combinatorial type, which means then if I can say anything special about my root polytope, right, that's really inherent about the polytope itself, then that's a trait that matches onto the valuation polytope. So for example, the volume, same volume. If I can talk about the Earhart theory, it's going to be the same for both polytopes. So in some sense, understanding this root polytope over these special graphs is like understanding the valuation polytope. All right, so for the last little bit of my time here, I want to dig in deeper into this H star polynomial question, which again came from looking at the generating function of our Earhart polynomial. And thanks to Stanley, we actually have a really nice description of what the coefficients of this polynomial look like. So if you have your polytope P, and you know that there is a unimodular triangulation for that polytope, then your H star polynomial is actually equal to the H polynomial of your triangulation. This is just a sort of way of encoding the different facets of your triangulation, this H polynomial. But furthermore, if you can take your triangulation and show that there's a special ordering on how you add simplices or faces of various dimension to your triangulation, we call that a shelling. So if there's a proper shelling order of your triangulation, then in fact you can describe the coefficients of your H star polynomial even more precisely. So it turns out that with this shelling, H star sub I, so the ith coefficient, is equal to the number of full dimensional simplices that are added along I of their facets in the shelling order. So this kind of gives you a nice way then to sort of think about how might I want to describe, or how could I actually give to you a description for what this H star polynomial looks like. When we think about a shelling, you can sort of think about that as a way of like inductively building the boundary of your polytope. We'll just say it that way since I have it here. But now this sort of gives us a goal. So if we want to actually think about how to describe this H star polynomial, what we need is a shelling of a triangulation over our root polytope, right? We're going to stick with the root polytope. We know whatever we say for that will hold over for our valuation. So that's going to be our last goal for the talk today. All right, so in order to come up with this shelling, we first need to give a good description of what this triangulation looks like. All right, so recall, right? The root polytope comes with a graph already. So it turns out, which is a very nice result, that all the simplices possible in your root polytope correspond to what we call a spanning tree on the acyclic oriented graph. So if you're not familiar, a spanning tree is going to be a collection of edges such that all the vertices of your graph are contained in your tree, and there are no cycles in that collection of edges. Okay, so you see all the possible spanning trees for the root polytope with this associated graph. But we know that there should only be three simplices that we want for our triangulation, like we saw before, right? Here's the triangulation from the valuation polytope. So we know that we're only looking for three simplices over here. And of course, I've highlighted the ones that I like in green. These are exactly the three spanning trees that would correspond to those simplices for the valuation polytope. So we need to make sure we know how to describe those simplices so that we can add them properly in our shelling and then count them up. All right, so we're able to show that the simplices are of three types. So if you're considering just the poset of odd number of elements, I should be clear on that this is going to be the zigzag poset with odd number of elements, that you're guaranteed to have the simplex in this special triangulation be of one of these three types. So if I have, a spanning tree of some number of edges or vertices prior to the last two vertices that I consider here, I'm going to look at these three vertices in the graph here. And then I just look for how do I complete my spanning tree from before to include these last two vertices. And I'm going to do it in the following three ways. So either I complete it by adding two edges to the sink, which is the same as saying I do not include these two edges above, which is why I think about putting a 0 here. 0 here means I do not include these two edges. Or I can include this outer edge to the sink and only include this one edge here, which is why I put a 1 here. So this 1 indicates I've included this one edge here. Or I include both of the edges. So I have two options, right? Two edges I can include here, which is why I put a 2 in this index here. 2 here means I've included these two edges. So sort of recursively, we can see how we might describe our simplices used in this special triangulation. And I say special because it's a particular triangulation that we've chosen for our root polytope. It's the same one that we used when we proved the when we proved the volume formula for the zigzag valuation polytope. All right, so for example, if you take the simplices of the excuse me, of the root polytope with the zigzag over with three elements, then that each one of the simplices that we have here will correspond to the spanning trees that you see above, right? So S sub 2 means I included the two edges up top. S sub 1, I only included that one edge. S sub 0, I didn't include any of the edges. Great. So now to move to the next odd dimension, right? This is a result only about odd dimensional root polytopes over zigzag with odd size. Then I keep each one of these spanning trees as my sub-spanning tree here. And then I again just say, did I include those two edges? Did I include only the one edge, or did I include no edges? And so that's where these subscripts come from. 2, 2 means I included the 2 here and I included the next 2. 2, 1 means I included 2 here and I only included the last one there. I included 2 edges. I didn't include the last 2, which is why I write 2, 0. Okay, so I hope it's clear how we encode the edges included and the spanning tree in the sub-indices here for each simplex. All right, and we're already kind of seeing that there's some structure to how these simplices are aligned, right? They're adjacent to one another when there's an edge that's turned from on to off or from off to on, right? So there's an edge in between these two simplices, meaning these simplices are actually adjacent in the triangulation, which is really, really important because now for shelling, we need to know how are we going to build up our polytope by sort of connecting each one of these simplices together. It's kind of like a game of Legos. We take a simplex, we attach another simplex. Now we're going to add another simplex. And anytime I add a new simplex or like add a new Lego, I can only do it along a maximal face. Okay, so here we go. Luckily, we had a guess for what this looked like. So here's our guess for what the polynomial looks like for odd dimension root polytope. And this gives us then sort of a guiding light, right, of what the coefficients should look like. So the kth coefficient here is going to be, or excuse me, the ith coefficient here is going to be this k choose I 2 to the I. So we're already thinking, at least I'm already thinking, okay, this looks like a set of k things. I've chosen I of them, and every one of those I things has two options. Okay, so with that in mind, let's run through the algorithm that describes the shelling. And hopefully you'll already start to see how this count is showing up in the algorithm. So this first simplex we're going to add in this shelling algorithm is the simplex that has all the edges included in the subtree. So we've got, for example, this one, or the S with all twos. And then next, we're going to choose an index. We'll call it I. We change that I to 1, which means it's now adding the simplex that has just that single edge, or simplex associated to the spanning tree with just that single edge, like this one here. And then we change that index to 0, which means we remove that last edge, or attach the simplex that looks like sub 2, 0. Okay, so we kind of like found our way across already top, but we could have chosen the first sub index and changed it from 1 to 0. And then we can go down here. Once we do that, now we're going to choose 2 sub indices to change from both to 1, then both to 0. And every time we're changing an index, it's like we've adjoined that simplex in this creation of our polytope. And so then the next step after that is now you're just choosing subsets of the indices of larger size. So instead of choosing 2 indices, you choose 3, and then you choose 4, and then you choose 5, but you still incrementally decrease the value of those indices, just like we did here. We chose 2, then we decrease them to 1. Those same ones we then decrease to 0. And then at the very end, you're going to choose all the indices, right? You've changed to 0. That's the last step there. Okay, so why is this helpful? Well, because if we're careful, right, to think about what the algorithm is telling us, is it's saying among the k indices that you have, choose I of them, and then they have a choice. You either choose that index to turn to 1 or to 0, and that's where the 2 to the I comes in. Here's just another example of how this looks if you apply the algorithm to dimension 7, just so that you can see that there's actually options to choose sets of larger size of the indices. All right, but so now that we have that, like I said already, the simplices are added along their faces, and we're just trying to count along how many simplices are added along I of their facets. And like I said before, we're choosing subsets of k things, of k indices of size I, and each one of those indices has an option to change to 1 or 0, which is this 2 to the power I. And so we've shown exactly that the coefficients are counting what we expect. And so then now we have that the H star polynomial is exactly what we want it to be. Okay, that was for the odd case. What about the even case? Well, luckily we have a nice result that says if we're looking at a bipyramiding over a polytope, then that Ehrhart polynomial is just the Ehrhart polynomial of the original polytope times this nice rational polynomial here. So then from there, we're able to say that the H star polynomial for the even is going to be the H star polynomial for the odd times just that 1 plus z. All right. So we've got a nice description for the H star polynomial for both odd and even cases of the zigzag valuation polytope. From this, we can see that H star is real rooted, and so it's actually unimodal, which is a really nice result. And then we can kind of jump all the way back to that long list that I started off the top with. That was like, here are some things you might ask if you're interested in looking at a polytope. For just the zigzag, and then we have some preliminary results for bipartite posets, where we're able to give a description of facets and vertices, talk about volumes, look at the H star values, and look at triangulations and how they are actually related to these spanning trees of acyclic oriented graphs. All right. Some other things that we're working on now is most likely still sticking with this root polytope perspective to try to describe the triangulation maybe in a non-recursive way. Maybe there's some nice canonical way that we could do this without having to depend on that recursion. We'd like to finish describing the rest of the values of the F vector, and then determine a minimal inequality description, which means looking at the hyperplane description of our valuation polytope and removing any redundant inequalities. So that would be something that would be great to have. And then, of course, how can we move beyond height 2 posets? And since we know that we have oriented graphs associated to these things, actually that gives us a way into talking about oriented matroids and maybe other matroidal results. So that's also a direction we've been thinking. And I just wanted to end with a few different sort of open directions that people might consider if this is at all interesting to you. So if you have a poset that you're excited about, some things that I wrote here, but absolutely, and any poset that you're interested in could be great. Matroids come with a lattice of flats. There's something called sign posets. Certainly other posets that have nice structure like a Boolean lattice, they are going to be complicated. I think that might be one reason why this question has stayed open for so long, is because even height 2 seems pretty challenging. So I would say and imagine that any poset of larger height is going to create lots of complexity. But we also know that Stanley showed the H-star polynomial of evaluation polytope respects poset addition. So this is a result that you could look up in the EC1 book. So it just asks, like, are there other poset operations or properties that maybe the valuation polytope can see or recover or somehow encode? I think that's a great direction to consider. And then one might ask, just sort of thinking about like maximizing or minimizing information about the F vector. There's some results already out there. Is there maybe a poset structure that does the same for the F vector of the valuation polytope? Can we sort of describe what that poset might look like that maximizes or minimizes this F vector? All right, well, I want to thank you so much again for taking your time to watch the video. I look forward to talking with everybody at our meeting, and please ask questions when you see me or via email. That'd be wonderful.